Okay. This topic here is kind of a biochemistry topic. There's a lot of overlap with biology, and since I don't teach you guys biology at all, I need a little bit of help. For you guys in grade 12, you've talked about catalyst at some point before in biology. Could you give me a very, very quick synopsis of like what a catalyst would be from a biology point of view? I'm willing to be brave here. Okay, that's pretty much all I need for you guys to know. Yeah, let me actually write down Rebecca's exact words there. There. If you've never heard of a catalyst before, it helps a reaction. What did you say? Happen or start. Okay, that's basically the concept of it. You guys in grade 11, you haven't gotten far enough to talk about catalysts yet. I'm guessing, right? Do you guys know when you learn about this in biology, grade 11 or 12? Okay. So you'll probably hear about this, you guys that are taking bio right now. Basically, the concept is that we could write a reaction down on paper, and in a second here, I'll just make up a fake reaction here with like pretend letters. And in theory, it should make sense because all of like the chemistry works out. Like both sides are balanced, the equation makes logical sense, and yet for whatever reason, the reaction does not occur. And we're going to spend a little more time over the next this section here, plus some questions in our next unit, where we talk about reactions that, for whatever reason, they just don't happen. But we change one parameter. Sometimes we do something like we change the temperature, or we change the pressure, or we increase the concentration, or in this example here, we add what's called a catalyst, and all of a sudden now the reaction happens. And we go, well, why did it all of a sudden happen now? Like, what was the main difference? And there's actually a chemistry mechanism that I want to explain today. But let me just make up like a pretend example here first. So hypothetically, you have A plus B, and you want it to turn into C plus D, and like everything is balanced, right? Like the equation, everything on paper makes sense. I'll give you an example here. Let's take CH4. We add O2. We want to turn it into CO2 and H2O. You guys all know this equation. This is the combustion of methane. Right? Here, there's some methane just sitting on the table there. Why is it not exploding right now? Yeah, what's the chemistry word we learned yesterday, though? You're right. What sort of what do we call the spark? Say it. Yeah, we need activation energy. Yeah, that's the word we're looking for. Yeah, you can call it an initiation amount, but yeah, you need to get over that barrier. If I were to draw this in a graphical format, we know that this is going to be an exothermic reaction. I should also balance it though. Hang on, it's not balanced yet. We did two there and a two there. Okay, now it's balanced. We know this is an exothermic reaction, which means that however much energy that we started with, we are going to lose, finger quotes, energy, because that energy is going to be released to the surroundings. Right? And so we know that the graph is ultimately going to start at, say, 100 and end at 50, and thereby we're going to have a delta H of negative 50. Does that make sense? But reactions don't just spontaneously happen. All reactions, like literally every reaction, has to get over the initial activation energy barrier. Why? In order to get over the activation energy barrier, what's actually happening? If you could hop on the magic school bus, zoom down to the level of atoms, why? And what does the collision cause? You're getting there. Bond stopping. There we go. Well done. Got a roll today. Yeah. So we need to draw our diagram just a little bit differently. We need to draw it more like this, where there's a section up like this, and then it goes downhill. Where right here we're having bonds breaking, and right here we are forming new bonds. Okay, that was basically yesterday's lesson in a nutshell. Now let's bring this back to catalysts. There are some reactions that I can write them down on paper, but they don't actually happen until we add something else to make them go. And so a catalyst provides, in chemistry, we call it an alternate pathway. And essentially what it does is it lowers the activation energy. I want to go back to Rebecca's definition here. Okay? When you learn about this from a biology point of view, she said, sorry if you can't read my chicken scratch writing here, it helps a reaction to happen or start. Well, why would a reaction not happen or not start? Well, it has too much of an energy barrier. There's too much like of a wall in the way. And what a catalyst does is it finds a way to decrease that amount of energy required. Does that make sense? So most of today's lesson is actually a bunch of pictures. I'm going to come back to my first slide here because it's a lot of words and it's really boring. Let me go to all the pictures that I've got here, try to explain things. Okay, so here's a basic picture involving pathways. This is an exothermic reaction. If you use what's known as a catalyst, basically all you need to know from a chemistry point of view is that it lowers the activation energy. Okay? Look at our start to our finish between the yellow and, or what is that, orange and green reactions. Isn't the change in enthalpy the same in both reactions? But which reaction would be easier to perform? Well, clearly the green reaction, because there's less of a barrier in a way, that activation energy, there's less of it. That's what a catalyst does. So a catalyst is a chemical you add to an equation to make this work. Just so you guys are aware, it usually looks like this. If you have an equation, A plus B forms C plus D, if we ever need a catalyst, we usually write it on top of the arrow. H2SO4 is a common catalyst, sulfuric acid. And we write it on top of the arrow. And what this means then is that it's not actually a reactant, and it's not actually a product. It's neither. But it's like an extra something we throw into the beaker in a way. And when we're done, we're actually going to have that catalyst still there when we're finished. It's almost like you throw it in, it reacts, but when you're done, you're actually going to end up with the catalyst back again, so it does not itself get consumed. Therefore, it's not actually a reactant or a product. It's because some kids would ask, well, why don't you write the catalyst as like an extra reactant? But that's not really how it works. A true catalyst is a reactant, but you'll also end up with it as a product. So like whatever you start with, you'll also end with. And so there's no point in writing it on both sides, so we usually write it on top of the arrow. Does this make any sense so far? It's really challenging because it helps if you have a little bit of biology background, because then you'll see that catalysts are used in a lot of enzyme reactions. So, here's kind of another diagram that I can hopefully help use to describe things. Imagine that you have a chemical reaction, and this one here is endothermic. Okay. Hopefully it's obvious to you guys that it's endothermic. One thing about endothermic reactions is they always have a high activation energy barrier. Right? Like look at this example right here. If it's going to have to go all the way up over the hill and then back down again and still have like a net upwards amount, you're going to have a high activation energy. In order to overcome that, sometimes that's not very easy to do. Maybe we don't have enough oomph to make the chemicals work. So this provides, the words we often use are an alternate pathway. I'm going to show you this picture here in a second. Okay, it's probably 2 slides away from you guys, right? Can you kind of like flip back and forth between these two? So I'm going to go back to this one here. You guys look at the one that's on your page. Can you see how from the start to the finish, the one that's got like a series of like curves in it is actually the same start to finish. It's positive 28.7. That's what the other one is there, right? But what ends up happening in a catalyzed reaction is sometimes there's like smaller subsets taking place where it still starts and ends here, but it goes up here to here. That's one reaction. Then it goes from here to here. That's a second reaction. It goes from here to here. There's a third reaction. At the end of the day, from start to finish, can you guys see how from here to here, the start to finish is actually like in the same spot? However, through like a series of smaller steps, by using what's known as a catalyst, it used to require this much activation energy. But if you go to the one you guys should have in front of you, it used to be this high, but now what's the maximum amount you needed? Well, it's only this much here. Does that make sense at all? So, long story short, what you guys need to know is a catalyst decreases the amount of activation energy, somehow. Somehow it does that. The other thing you need to know is that catalysts themselves are not consumed by a reaction. So if you begin with it, you have to end with it. We're going to use a catalyst in one of our future labs. And so one of the downsides to just the way the curriculum is organized is that I will show you a catalyst, I promise, at some point. We're actually going to use sulfuric acid to make a reaction take place. And one of the cool things about it then is that when we're finished, we still have sulfuric acid, and we actually have to find a way to separate it back out again, which actually makes the chemical quite dangerous, because if it wasn't for the sulfuric acid catalyst, the reaction would be something we would actually taste and eat, believe it or not. You guys have probably smelled my esters lab before in the previous building. Okay. Some of them are actually very pleasant artificial odors and tastes. Like we can make, say, like an orange taste or raspberry flavoring. Those would be safe if it wasn't for the fact that when we do this lab, it's about a month away or so, we use a catalyst of sulfuric acid, which means that when we're done, there's H2SO4 still in the reaction. So, In terms of this picture, I want to go back to I need to flip back and forth. I wish I didn't put a slide in between. Okay, if you guys can kind of see these pictures right here, in the uncatalyzed reaction, we've learned now that molecule A and molecule B need to literally crash into each other with a collision, and that collision is then useful for breaking bonds. Does that make sense? It has to have a sufficient amount of energy, has to have the right orientation. But what if that's just too much of a barrier? What if that's just too high for it to take place? Well, if you flip then to this equation over here, what we've done instead here is we're adding this extra little molecule. In this example here, it's just a blue dot with a positive sign on it. Okay. Well, what if we add a catalyst, a third compound? This catalyst then crashes into this guy, forming this one. Well, then this one breaks into two pieces. Well, then this one rearranges into these pieces. And one thing I want to point out, see how you started with this catalyst right here? See how we've finished with this catalyst right here as well? That is a key component of it. It is both a reactant and a product. And through essentially Hess's law, we can find a way to like piece together the exact same starting and finishing reactants and products, but there's an alternate pathway. That's the word we use. I want to flip back a slide here. I should really reorder these one here to this one here. Imagine that you had this sort of scenario here, where you had some reactants, and then you wanted ideally your reactants to go to products. Like that's normally how things work, right? Reactants go to products. But for whatever reason, from reactants to products, too challenging of a barrier to overcome. Well, what you could do is this. Reactants go to an activated complex and then an intermediary. Then the intermediary goes to an active complex and a second intermediary. Then that goes to a third activated complex, and then finally your products. What I'm describing here is effectively this picture. Here is our reactants, turned into an activated complex and intermediary 1. They went to an activated complex and intermediary 2. They went to an activated complex and then finally finished with our products. So long as the highest intermediary part you get to is lower than what it would have been, you now have a catalyst. Long story short, it makes an equation, it makes a chemical reaction happen better, quote unquote. Okay. As you learn about these more from like a biology point of view, hopefully that'll like fill in the gaps, because you guys have talked about this at some point. So 2 things if I had to summarize this. What does a catalyst do? It lowers the activation energy barrier. Okay. Somehow it does that. And secondly, catalysts themselves are not consumed. They are not products or reactants. We add them in, but if we start with our catalyst, we better be able to literally reach into our beaker when we're done and take the catalyst back out, or like filter it out, or do something to remove it. But it itself is not actually part of the equation. It just helps find alternate ways of getting there. And one of the unique things about catalysts is there's so many different types that I'm being very, very general right now. If it feels like I'm not telling you a lot of information, that's actually on purpose, because lots of different reactions have different catalysts, and they all work slightly differently. But those are the 2 things they all have in common. Easier to make a reaction happen due to less activation energy, and they're not actually consumed in the reaction themselves. Does that make sense? It's a very theoretical type of section. Why don't I go back to that very first slide that I kind of skipped, and I'll see if there's anything relevant on here I need to add. Yeah, basically this right here is what a catalyst is. A catalyst is a substance that increases the rate of reaction without itself being consumed. Rate of reaction, that's maybe another fancy way of saying, does the reaction happen quickly? You know how some reactions take like, bang, they happen like in a second, and some reactions take years, like say rusting takes a long time. A catalyst just speeds things up, it makes it more effective. Oh, here's another important thing. Catalysts do not alter the net enthalpy change. I want to make sure I'm clear on that. When I showed you guys these 2 pictures here of catalysts, see how this one here went up by 28.7? And in this one over here, it still went up by 28.7. The only difference is it didn't have to reach quite this high. It only had to reach this high. One last thought, then I'll be done for the day. Maybe as an analogy, Anybody ever traveled to like say the Vancouver Island to the coast by car? It's something that I did a lot. I grew up in the mountains in BC. And so if I had to kind of think about how to get from Cranbrook, where I grew up, to Vancouver, I mean, if I go from Cranbrook to Vancouver, here's my start, here's my finish. But there's different ways of getting there. For example, the most common way of getting there is to take, if you guys know your travel, Highway 3. You guys know Highway 3? It basically is what I drive every day here. It keeps going basically from here all the way to the coast. One of the downsides to that, though, is that you literally have to go up and down all sorts of mountains. Right? If you've been to the Creston Salmo Pass, anybody ever heard of that before? Creston Salmo? Huge, basically huge uphill. You basically go all the way up one side of the mountain and all the way down the other side of the mountain. It's very inefficient because rather than going this way, you're going this way and this way. I'm doing up and down. Okay. So that's one path you could take, and that would require a lot of activation energy because you have to reach quite a high distance. Another option is you could actually travel through the United States. And so if you go down into the United States and then take its I-90, you basically can go through like Montana and Washington. You go down south, and then you come back up through Seattle. The nice thing about that one is that then you don't have to go quite up over top of the Rocky Mountains. There's a little bit more of a sideways path. You kind of get the analogy I'm going with here? One of them ends up requiring a lot more height distance than the other one does, but at the end of the day, don't I end up in the same spot? Okay. So that's maybe my analogy here, is that this one right here has quite a high mountain to traverse. And if I don't kind of want to go all the way to the top of one high mountain and come back down again, then maybe an alternate pathway would be to take smaller series of mountains. And so I don't reach quite the same maximum height, but I still end up my start to finish in the same spot. All right, any questions? What's my time out here? I do it in 10 minutes or less? Oh, this wasn't even close.